Well, 9 times 16 is 144, plus 10 is 154. That's what's actually in the exponent field. But remember that what we're actually storing there is the exponent plus 127. So to get the exponent that we want in the number, we have to subtract that bias, it's called, 127. Here's 2. Okay, so the actual exponent is 2 to the 27. In both cases, that hasn't changed. So let's see. What's my number? I've got to move that point 27 places to the right. So I've got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, 25, 26, 27. Point. That's the number that I've got in there.
So there's 25 zeros?
I think there's more than that.
26 zeros.
Because I moved from here one place in. Yeah, they're 26 because I moved it 27 places. This is a 1 and all the rest of them are zeros. Okay? In other words, it's an integer. It has no fractional part to it. There's nothing beyond that point. Let's see what it is. Okay, in hexadecimal, it's C, 1, 2, 3, 4, 5. Or, in other words, it's 12 times 16 to the 0, 1, 2, 3, 4, 5. 12 times 16 to the 5th power. Okay, we're going to cheat. Rather than trying to calculate 16 to the 5th, we'll use the calculator. Just as a side light, that's 12 times 1048576.
How come it's not 12 times 16 to the 6? Yeah, 6 sets of 4 zeros.
No, there should be 6 zeros, not 5.
Because this is times 16 to the 0, 16 to the 1st, 2nd, 3rd, 4th, 5th.
Oh.
Remember, you always start at 0 because that units digit down there is always times 1, which is the base to the 0 power.
Why is there 5 zeros, not 6?
It should be 6 zeros.
There should be 6 zeros.
1, 2, 3, 4, 5, 6. You're right. Yeah, that number is a little small. 0 in hex, so it is times 16 to the 6th. And let's see. 12 times that. It's 201,326,592. Okay. Now let's look at this next larger number and see what we get here. Let's see, in between I've got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21 zeros. So my number here is 1, 1. 1. Okay, now how far have I come? I've I've got 21 zeros. 3, 4, 5, 6. 21. This place makes 22 and this one makes 23. I've got to get up to 27. 4, 5, 6, 7. Yeah.
I'm a little confused on something, just going a little bit back. You split the hex into binary, and you separate the exponent.
Mm-hmm.
Now, you got, after the exponent, 1 followed by a ton of zeros.
Mm-hmm.
How did that become 1.1?
Because in this format, there is always a leading zero that is not stored. It's put back in there by the software when you do the calculations. They do that to kind of cheat and give you one extra binary digit. It's what we call normalization. The number is always normalized so that it's in the form 1 point something times the power of 2. And since it's always 1 point, we don't need to store the 1. We just recognize that it's there.
Okay, so 1 point is an antecedent.
Right. There are a couple of exceptions to that in specific cases when the exponent has a certain value. Then you don't assume that leading 1. But in every other case you do. Okay, so what have we got here? We have in hex, we've got C, 0, 0, 0, 0, 1, 0. Converting that into base 10, again, this is 16 to the 0, 1, 2, 3, 4, 5, 6. So we've got 12 times 16 to the 6th. But now I've got this thing. It's actually 1 times 16 to the 1st. And so I end up with this number plus 16 would be 608. Okay. Have you figured out the significance of all of that? I cannot represent exactly the number 201,326,595. I can't represent it. I don't have enough bits. I can't get anything between these two numbers. I just can't.
About 591.
Nope.
So it's
If you look at the next smaller number, it gets more complicated.
never mind.
But there's a gap in there. And the farther up you go, the bigger that gap gets. The bigger your numbers are, the bigger the gap. Because you see what's happening is that when this power reaches 23, anything beyond that is just filling zeros at the end of the number. Because you can only store 23 places. Now, the same thing happens through the whole spectrum. It's just that the differences end up being quite a bit smaller. It's kind of interesting to look at this one. You cannot represent 1/10 exactly. You can't do it. Because in binary, 1/10 is a repeating, non-terminating decimal. You have to chop it off someplace. Remember in decimal, in base 10, 1/3 is non-terminating. If you work with it as a decimal fraction, you're only approximating. Same is true of 1/10. It's just there. These are the kinds of things, some of the principal reasons why every computer science student has to work at this level to really understand why, at some point, you get these bizarre errors that appear. If you try this little bit of code, yeah, let's go here.
Is that a 5?
It's an S. Let's see, where are we? Tens, hundreds, thousands, 10,000, 100,000. Yeah, we don't have commas here. Oh, let's not do printf, let's just see out. S. Oh, those go the other way, don't they? I don't write C++ much. Will you get a 1? Probably not. Because the difference there will be such that the inaccuracy in representing that 1/100,000, when it's multiplied by 100,000, gets to be significant. It shows up. Why? Because of this problem.
Is that just with the floating point?
Yeah, integers, of course, are different. Although you're well aware that there's a limit on the integers. You can add two positive integers together and get a negative result. Overflow, they call it. It's a different problem, but it's all tied into the way in which the numbers are represented. It's just there. Okay, anyway. Any questions? Okay, we're looking at the final exam, which is Monday morning. Monday is the 25th at 9 o'clock, and it will be here. And we're trying to settle on chapters 4 through, is it 9 or 10? 10. A slight emphasis on the end.
Which would be 8 through 10?
Well, let's see, where were we on?
Because the first
Last
half was
exam.
4 through 7.
The last exam just went 4 through 7? Certainly is. Yeah. Let me make a comment about I/O. On the I/O stuff, don't memorize the addresses.
Just what I was writing down.
That is the keyboard status register, the keyboard data register, display status register. Do know the busy wait works. Okay, this business of checking these status registers until you know that the device is ready. That aspect of it, you do need to know. But any need for those particular registers, I would give you the actual addresses that you work with. The other thing that comes out of this, associated with this, is the indirect addressing. Okay, there are only two instructions that use it. Load indirect and store indirect. Those are the only two instructions that use indirect addressing. But be sure you know how that works. The idea is that if I say, for example, okay, we'll pick on the keyboard status register. What the indirect does is it goes to this location and uses the contents of that location as an address. In other words, it makes two jumps in memory to get to the thing that you're looking for with the instruction. Yeah?
Is that considered an offset, like in binary?
No.
There's no.
It's not added to anything. It's not an offset. It just strictly uses the contents of the memory location with label KBSR. It goes out and it finds that, uses the contents of that memory location for another jump into memory, and then brings things in. Yeah?
Will you, like last test, will you have a list of the opcodes and stuff?
Yes, I'll give you the instruction set. Yeah.
Awesome.
And also the ASCII table if it's needed. Yeah. Haven't decided yet if it's going to be needed or not, but we'll see. Nobody memorizes the ASCII table. There are certain values, of course. We know it's easy to remember that the digits are just 30 plus the digit. So at 5, the ASCII code is 35 in hex. Those are easy. The rest of them are not. No logic behind it. Okay, so that comment on the I.O. chapter, look for that. Let's see. The next chapter has to do with subroutines. So what we're concerned with there are these two instructions, how they work. Related to that, then, how to pass arguments. And there are a couple of significant ways. The usual first one is to use the registers, but that's limited. You can only pass, you can pass no more than 7 values through the registers. Because the 8th, if you put anything in register 7 and then do a JSR, what you had in register 7 is gone. Because it gets replaced by the return address. So you're kind of limited.
I
There have to be
also
other ways.
noticed that the out routine modifies your R7 as well.
Yeah.
Yeah.
There are others that use it. Be very cautious about register 7. Yeah.
When you say arguments, I don't understand what you say. What's your
Oh, when you call a function,
Parameters.
let's say,
Parameters.
Well, to use a C kind of thing, you have a function, these are the arguments.
Okay. Different terminology.
Okay, that's the kind of thing that we're talking about.
I don't even know function prologues on it.
The second scheme is to just use memory. That really, what you're talking about there are global variables. The original BASIC language, for example, used this scheme. And so if you wanted to, just to use a linear algebra example, if you wanted to find the length of two different vectors, you would have to position one of them, let's say, in A, call the subroutine, and then to do the other one, you would have to move the values for your B vector into the same memory locations because that's where the subroutine expected to find them. It was really awkward, really a kind of a miserable way to do things, because one case you have to look at all the elements of the vector A, and in the other one you're looking at the elements of the vector B. And if you can't change that variable name in your code, you're stuck. Okay? So the more common thing, well, is to put values in memory, in a memory block, basically, and put the address in a register. This is still basically the way C and C++ and C# and the rest of them handle passing arrays. Rather than making a copy of that whole array, they just say, okay, this is where it begins, go ahead and use it. And you can change then where it begins, look at different places. The fourth one, which gets us into the last chapter, is to use the stack. For everything except arrays, and even to some extent there, this is the way the high-level languages, all the C languages, Java, all the rest of them, that's how they do it.
On number 3, is that like using the block word and then?
Probably,
And then
yeah.
put the address of the first block word
Yeah.
in the register?
You see, you might have, for example, if you've got an array, you've got a 10-element array, and then you've got another one, and you've got a function, a subprogram that finds the sum of all the values in that array. Well, the way you could handle that using this is you would say, load effective address A, well, register 0, A, and then go to your subroutine, and then do something with the result, and then you can load the address of B into register 0 and go to your subroutine again. And that's the idea. Again, common practice. You have to realize that you're telling the subroutine where that array is. And so any changes made in the array by the subroutine will be reflected in the main program. Does that happen in C++? Nod yes, it does. It's exactly how it works. It's exactly what it's doing. But on the other hand, if you have a function like I just had down here where you have two integers that float, you change those in the subprogram, does it change in the main program? No. Because they're passed differently. They're passed using the stack. It's this pass by reference, pass by value. Those are the key words. This is a pass by reference. I am giving a reference to where the data is. When you push things on the stack, you are saying, here are the values to work with. These are the actual values. Okay, and so that leads in, of course, to the chapter 10, which has to do with the stack. One of the things to recognize on the discussion about the stack in there, they use register 6 consistently as a stack pointer. That isn't absolutely required. It's somewhat under your control on this machine. That is not always the case. But it is a good idea, good practice to be consistent. So that you're always using the same one. And traditionally on a lot of machines, that's the way it is set up. Register 7 is the highest numbered register is often the program counter, and the next one under it is the stack pointer. Just typically the way they choose to do it. Point being that some assembly languages will actually have push and pop instructions as part of the assembly language. When they have those, they function just like the JSR. They always use the same register. So, just be in the habit. Okay, that's kind of a quick run through. What do you want to look at? Want to look at any particular things out of this? Yeah.
Passing values to a subroutine using memory.
Oh.
I'm hazy on that. We just see.
Let's see.
a quick example.
Let me see. Let's do it with one where we wouldn't have to use that. We could pass the value in the register. We have a subprogram here that finds the square of the argument. Okay, now if we pass in the register, we would do the following. We would load, let's say, register 0 from X, and jump to our subroutine to find the square. Our subprogram would begin then by, well, rather than attempting to write anything down here, we would just multiply register 0 by itself and then do a return. Okay? Now, if we pass in memory without using the address, let's see. What I wanted to do here was follow on with a load register 0 from Y and do another JSR. Do two of them, that's where it makes a difference. If we just pass in memory, then our subprogram over here would look like this. Load register 0 from X, compute square, and return. Now, in order to get the second one done, I would have to do something like this. Load register 1, Y, store register 1 into X, and then do a jump to my subroutine. Because the subroutine has a hard-coded memory location. Always going to find it in this memory location. Now, it's almost never done with a single value, of course. But think array again. What you would have to do is go in and work with the array X and do whatever your function's doing with it. But then you would have to copy the array Y into the same locations as the array X and call the subroutine. Because it says, I'm always looking in this piece of memory right here. Kind of an awkward way of doing it. Okay, what it comes down to is that we're talking global variables. Now, the third option down there is a better one, where you would X, and now in your and then call our routine. This says that the address of what I'm looking for is in register 0. Okay, we can use a load relative. No offset, just use register 0 as an address, load register 1 from that. Okay, compute, return. We would do something over here with the result, do Y. We would do this. Okay, much better approach. This is probably the weakest way of doing it. Probably the weakest. Like I say, the original BASIC back in 1964, is that when BASIC was first introduced? I don't remember. It had a subroutine call, but this is the way it worked. It was really awkward. Not a very efficient way of doing things at all. Okay, but the big thing about subroutines, subprograms, the whole purpose of the thing is to write code that you don't have to repeat over and over again in your main program. And so the whole essence of the problem is passing arguments. Once you get your arguments passed, the rest of it works out all right. Okay? Other questions?
So,
Yeah.
you load just following what you did, kind of load the register and the address, what kind is that? Is that using not the stack, the other one?
Yeah, that's number 3.
Okay, that's what I thought.
Put the address of the memory location in a register. Okay, the basic format of the test will be just like the last one. There will be a number of short questions. There will be some code for you to read and say, what does this thing do? What does it leave in some register? What does it print out? You know, something like that. What's the result in some way? Please show your work. I will emphasize that again on the paper. It really disturbs me when I come across a problem like that and all I find is a written answer and it's wrong. Okay. There's nothing I can do. I can't help you in any way, shape, or form. It's just total loss. 0 points for the question. If you show me some work and I find that all you did wrong was you added 2 and 2 and got 5, you'll get most of the credit. Okay? So show some work, especially on that kind of a problem. Especially there. Trace the execution, see what's going on, see what's put in various locations.
So are we gonna have to write any problems?
That's what the course is all about.
What?
I don't know.
Is it more than the last one?
Yeah,
Just
because it's a
shorter.
2-hour exam.
Right.
Will it be twice as much? No, probably not.
What about the von Neumann,
Uh,
however the heck you say it?
Yeah, chapter 4 is part of it. Be aware of what's in there. Because it is the basis for what we're doing currently. There's a lot of discussion that we have about reached the limit on the von Neumann architecture.
So there's a lot of discussion on whether they're gonna